Right now, you are inside the Higgs field. You cannot see it, feel it, or detect it with any of your senses. But it is there, surrounding you, permeating you, filling every cubic centimeter of the room you are in, and extending, without interruption, across all of space in every direction. The Higgs field is not made of anything you can hold or touch. It is a quantum field, a fundamental feature of the universe that exists throughout all of space, much like how a gravitational field exists around every mass, or a magnetic field exists around every magnet. But the Higgs field is different. It exists everywhere equally, even in the deepest void between galaxies, even in the center of empty space, far from any particle of matter. The Higgs field is the reason you have mass. Every proton, every neutron, every electron in your body is constantly interacting with the Higgs field as it moves through space, and that interaction is what we experience as mass. A particle that interacts strongly with the Higgs field acquires a large mass. A particle that interacts weakly acquires a small mass. A photon of light does not interact with the Higgs field at all, which is why it has no mass and always travels at the speed of light, unable to be slowed or stopped. Without the Higgs field, all particles would be massless. Massless particles must travel at the speed of light. At the speed of light, time does not pass. There would be no atoms, because atoms require electrons to settle into stable orbits around nuclei, and stable orbits require mass and the slower-than-light motion that mass enables. There would be no chemistry, no molecules, no matter in the familiar sense. The Higgs field is not a detail. It is a precondition for the existence of everything you have ever touched or seen or known. This field was predicted mathematically in 1964 by Peter Higgs and independently by several other physicists. It was predicted on the basis of the mathematics of quantum field theory from theoretical necessity, decades before any experiment could test whether it was real. In 2012, physicists operating the Large Hadron Collider at CERN near Geneva collided protons together at energies high enough to momentarily create a Higgs boson, the particle associated with the Higgs field, a tiny ripple in the Higgs field itself. The detection confirmed what the mathematics had long suggested. The field is real. You are in it. You have always been in it. Tonight we go deeper than planets and solar systems and galaxies. Tonight we explore the cosmos itself, the underlying structure of reality, the laws and fields and forces that make everything possible. Not just the things the universe contains, but the nature of the container itself, the fabric of space-time, the quantum fields, the four fundamental forces, the deep logic of why anything exists at all rather than nothing. Everything I am going to tell you is as true as anything in science. These are the deepest things we know about reality, and I invite you to rest in them, not to analyze or memorize, but to let them wash over you, because there is something deeply calming about understanding the universe at its most fundamental level, about knowing that reality has this depth, this beauty, this extraordinary internal consistency. Take a slow breath in, all the way, gently until your lungs are full, and breathe out slowly, completely, feeling your body settle and your muscles release. You are in the Higgs field. You are in the gravitational field of the Earth, which is itself in the gravitational field of the Sun, which is in the gravitational field of the Milky Way, which is in the gravitational field of the local group, which is being stretched apart by dark energy. Every field, every force, every law of nature is operating around you and through you right now, continuously, without interruption, without requiring any effort from you. The cosmos is running. You can rest. The universe is made of fields. This is perhaps the most important and least intuitive insight of 20th century physics. Before quantum field theory, physicists thought of the universe as being made of particles, tiny indivisible units of matter moving through space. But quantum field theory revealed something deeper. The fundamental entities of nature are not particles but fields, continuous entities that exist throughout all of space and time. A particle is not an independent thing. It is a localized vibration or excitation in a quantum field, like a ripple on the surface of a vast invisible ocean. The electron, for example, is not a tiny ball of negative charge sitting in a fixed location. It is an excitation of the electron field, a quantum field that permeates all of space. Where we observe an electron, we are observing a localized excitation of this field. The photon, the particle of light, is an excitation of the electromagnetic field. The Higgs boson is an excitation of the Higgs field. Every particle that has ever been discovered corresponds to a quantum field that permeates the entire universe. The standard model of particle physics is the name for the collection of quantum fields and the rules governing their interactions that describes all known matter and all known forces except gravity. It is the most precisely tested theory in the history of science. Some of its predictions have been tested to a precision of 1 part in a trillion or better. The standard model describes 12 fundamental matter fields, 6 quarks and 6 leptons, and 4 force-carrying fields. Together, these fields and their excitations and interactions account for virtually all observable phenomena in chemistry, material science, nuclear physics, and particle physics. The 4 fundamental forces of nature are gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Gravity is the familiar force that holds planets in orbit and pulls you toward the center of the Earth. Electromagnetism is the force that holds atoms together, causes chemical reactions, makes light, and powers everything from the electric motor to the human nervous system. The strong nuclear force binds quarks together into protons and neutrons and holds protons and neutrons together in atomic nuclei, overcoming the electromagnetic repulsion between positively charged protons. The weak nuclear force governs certain types of radioactive decay, the transformation of neutrons into protons that occurs in beta decay, and is responsible for making the sun shine through the fusion reactions in its core. Each of these forces is mediated by a corresponding particle, the excitation of its force-carrying field. The electromagnetic force is mediated by photons. The strong nuclear force is mediated by gluons. The weak nuclear force is mediated by the W and Z bosons. Gravity, in the standard model framework, would be mediated by gravitons, though a complete quantum theory of gravity remains one of the great unsolved problems of physics. These 4 forces have very different strengths and ranges. The strong nuclear force is, as its name suggests, the strongest, holding quarks together with a force that actually increases as they are pulled apart, making it impossible to separate individual quarks under ordinary conditions. The electromagnetic force is about 137 times weaker than the strong force. Gravity is extraordinarily weak compared to the others, about 10 to the power of 36 times weaker than the electromagnetic force, which is why electromagnetic forces between atoms and molecules can completely overcome gravity at the scale of everyday objects, allowing a small magnet to hold a paperclip against the downward pull of the entire Earth. And yet gravity wins at the largest scales because it is always attractive and it accumulates over all mass. Electromagnetism largely cancels out at large scales because matter contains roughly equal amounts of positive and negative charge. The strong and weak nuclear forces have such short ranges that they operate only within atomic nuclei. So gravity, the weakest of the four forces, is the architect of the cosmos at the largest scales, organizing matter into planets, stars, galaxies, and the large-scale structure of the universe. Let your breathing settle a little more. The forces are working, the Higgs field is there, the quantum fields are vibrating, and you are resting in the middle of all of it. Quantum entanglement is one of the most counterintuitive and most experimentally confirmed features of quantum mechanics. It arises when two particles interact in such a way that the quantum states of the two particles become correlated and cannot be described independently. When particles are entangled, a measurement of one particle's state instantaneously determines the correlated state of the other particle, regardless of the distance separating them. If one particle is measured to have a spin pointing up, the entangled partner will be found to have a spin pointing down instantaneously, even if the two particles are on opposite sides of the galaxy. Albert Einstein found this deeply troubling. He called it spooky action at a distance and spent years arguing that quantum mechanics must be incomplete, that there must be some hidden variables, some underlying local reality that made the correlations appear instantaneous without actually requiring faster than light communication. In 1964, physicist John Stuart Bell proved mathematically that if Einstein's local hidden variable explanation were correct, the statistical correlations between entangled particles would obey certain inequalities. He derived what are now called Bell inequalities. Experiments beginning in the 1970s and continuing to the present day have consistently violated Bell's inequalities. Einstein was wrong. The correlations are not explained by any local hidden variable theory. Quantum entanglement is real and irreducible. Reality at the quantum scale is non-local in a deep, fundamental sense. This does not mean information can be sent faster than light through entanglement. The apparent instantaneous influence cannot be used to transmit information. And the theory is fully consistent with special relativity, but it does mean that the universe has a fundamentally non-local character at the quantum level. Entangled particles, no matter how far apart, are in some sense still part of a single quantum system. The separateness of distant things is not absolute. The uncertainty principle, formulated by Werner Heisenberg in 1927, states that there is a fundamental limit to the precision with which certain pairs of physical properties of a particle can be simultaneously known. The most famous example is position and momentum, The more precisely you know where a particle is, the less precisely you can know how fast it is moving and in what direction, and vice versa. This is not a limitation of our instruments or our measuring techniques. It is a fundamental feature of nature. Position and momentum are not simultaneously well-defined properties of a quantum system. The uncertainty is intrinsic. The uncertainty principle has profound consequences. It means that even in the lowest energy state, the ground state, quantum systems are not completely at rest. There is always some residual irreducible motion called zero-point energy. The quantum vacuum, the lowest energy state of the quantum fields that fill space, is not truly empty, but contains these zero-point fluctuations, constantly fluctuating between different quantum states. Pairs of virtual particles, particle and antiparticle pairs, constantly appear and disappear in the quantum vacuum. Borrowing energy from the uncertainty principle and returning it before they can be directly detected. This quantum vacuum energy is real and has measurable effects, including the Casimir effect, a tiny attractive force between parallel metal plates in a vacuum caused by the suppression of vacuum fluctuations between the plates relative to outside them. Now let us go back, all the way back, to the beginning. The Big Bang was not an explosion in space, it was an expansion of space itself. There was no point in pre-existing empty space where an explosion occurred. Space itself came into existence at the Big Bang, or at least the concept of space as we understand it began to apply. In the earliest moments of the universe, the energy density was so high that the known laws of physics, which require space and time to be well-defined smooth structures, break down. The Planck time, approximately 5.4 times 10 to the power of minus 44 seconds after the Big Bang, is the smallest time interval that current physics can meaningfully describe. Before the Planck time, quantum effects on gravity were so extreme that our understanding fails. What, if anything, preceded the Planck time is genuinely unknown. What we can describe is what happened after. In the first tiny fraction of a second, the universe was filled with a hot, dense plasma of all the particles and antiparticles of the Standard Model, created from the immense energy of the initial state. As the universe expanded, it cooled. A fraction of a second after the Big Bang, the quarks had cooled enough to combine into protons and neutrons. About 3 minutes after the Big Bang, the universe had cooled enough for protons and neutrons to stick together through the strong nuclear force, forming the nuclei of light elements, hydrogen, deuterium, helium-3, helium-4, and trace amounts of lithium. This process, called Big Bang nucleosynthesis, produced a universe of roughly 75% hydrogen and 25% helium by mass, with tiny amounts of the other light elements. The abundances of these elements, measured in the oldest stars and the most primitive regions of the cosmos, match the predictions of Big Bang nucleosynthesis theory with extraordinary precision. Then the universe entered a long period of darkness. For about 380,000 years after the Big Bang, the universe was so dense and hot that it was opaque. Light could not travel freely because it was constantly being scattered by the free electrons that filled space. Then, as the universe cooled further, the electrons were captured by the nuclei to form neutral hydrogen and helium atoms. This moment is called recombination, though it was the first time electrons and nuclei had ever combined. When the electrons were captured into atoms, the universe became transparent, light traveled freely for the first time. That light is what we detect today as the cosmic microwave background radiation, the oldest light in the universe, released at the moment of recombination 380,000 years after the Big Bang, and traveling freely ever since. After recombination came the cosmic dark ages. The universe was filled with hydrogen and helium gas, slowly drifting and gravitationally clumping, but there were no stars yet, no sources of light. For perhaps 200 million years, the universe was dark, filled only with the slowly cooling gas and the ancient photons of the cosmic microwave background, stretching to longer and longer wavelengths as space expanded. It was the quietest time the cosmos has ever known. Then, the first stars formed. These first stars, called population the 3 stars, or first stars, were very different from the stars we see today. They formed from pristine gas that contained only hydrogen and helium and tiny traces of lithium, with no heavier elements at all. Because there were no heavy elements to help dissipate heat through radiation, the gas clouds that collapsed to form these stars could not cool as efficiently as later star-forming clouds. The resulting stars were enormous, some perhaps hundreds of times the mass of the Sun, burning extraordinarily hot and bright and living for only a few million years before exploding in supernovae. These were the first sources of light in the universe since the Big Bang. The first stars ended the cosmic dark ages. Their ultraviolet radiation ionized the surrounding hydrogen gas, creating expanding bubbles of ionized plasma around each star or star cluster. This process, called reionization, gradually transformed the cosmic dark ages gas from neutral to ionized over the period from about 200 million to 1 billion years after the Big Bang. The universe became luminous again, this time lit by stars rather than by the white-hot primordial plasma of the Big Bang. And crucially, those first stars also began the chemical enrichment of the universe. Stellar nucleosynthesis, the fusion of lighter elements into heavier ones in stellar interiors, had begun. The first stars fused hydrogen into helium, then some of them fused helium into carbon and oxygen, then in the most massive ones, carbon and oxygen into neon, magnesium, silicon, sulfur, and eventually iron. When those enormous first stars exploded, they scattered these elements, freshly forged in their nuclear fires, out into the surrounding gas. The next generation of stars formed from this enriched gas, containing small amounts of carbon, oxygen, nitrogen, silicon, and iron, alongside the original hydrogen and helium, and those stars enriched the gas further when they died. This process of stellar nucleosynthesis and supernova dispersal has been running for the entire history of the universe. Every generation of stars has enriched the gas from which the next generation forms. The older the star, the lower its metallicity, the lower its content of heavy elements. The Sun is a relatively metal-rich star by the standards of the galaxy, meaning it formed from gas that had been processed through many previous generations of stars. And the planets that formed from the same gas as the Sun, including the Earth, contain the heavy elements that those previous stellar generations produced. The periodic table of elements is a map of stellar nucleosynthesis. Hydrogen and helium were made in the Big Bang. Lithium was also made partly in the Big Bang, though stellar processes contribute as well. Beryllium and boron were made by cosmic ray spallation, the breaking apart of heavier nuclei by high-energy cosmic rays. Carbon and oxygen were made in stellar fusion. The elements up to iron were made in stellar cores through fusion reactions. Iron and the elements near it in the periodic table are the end products of stellar fusion because iron has the most stable nucleus and no further energy can be extracted by fusing it into heavier elements. The elements heavier than iron, gold, platinum, uranium, and all the rest were made in the extreme environments of supernovae in the rapid neutron capture process called the R process, and also in the merger of neutron stars, a process confirmed by the observation of a kilonova event associated with the gravitational wave detection GW170817 in 2017. The gold in any ring on your finger was made in the collision of two neutron stars, and the explosion that followed scattered it across space, where it eventually became part of the cloud that formed the solar system. Every element in the periodic table has an origin story written in stellar physics. Every atom in your body was made in a specific nuclear process in a specific type of stellar environment. The hydrogen, the Big Bang; the oxygen, a red giant or a massive star; the carbon, the triple alpha process in red giant cores; the nitrogen, the carbon-nitrogen-oxygen cycle in stars; the iron in your blood, the final product of fusion in massive stars dispersed in supernovae. Let your breath slow and deepen. The elements that make up your body were assembled by the universe over billions of years in dozens of different stellar environments before they came together in the cloud that formed the solar system, the Earth, and eventually you, the cosmos, made you out of itself. Entropy is one of the most profound concepts in all of physics. In thermodynamics, entropy is a measure of the disorder or randomness of a system. The second law of thermodynamics states that in any isolated system, entropy can only increase or remain constant over time, never decrease. Things fall apart, ordered structures become disordered. Heat flows from hot objects to cold objects and never spontaneously in reverse. A dropped glass shatters into many pieces, but the pieces never spontaneously reassemble into a glass. The second law gives time its direction, the arrow of time, the reason the past is different from the future. In the context of the cosmos, the second law means that the universe began in a state of extraordinarily low entropy, a highly ordered state, and has been increasing in entropy ever since. The Big Bang state, despite being hot and dense, was remarkably smooth and uniform, and this smoothness represented a very low entropy configuration on cosmological scales. As the universe has evolved, structure has formed, galaxies, stars, planets, life. These local decreases in entropy are possible because they are more than compensated by entropy increases elsewhere, most notably the heat and radiation produced by stars. The sun produces light and heat, which ultimately represents the dispersal of ordered energy into disordered thermal radiation across space. Life on Earth, which maintains its complex ordered structures by consuming the sun's ordered energy and releasing it as waste heat, is entirely consistent with the second law. The ultimate fate of the universe, on the timescales we discussed before, is the maximum entropy state, sometimes called the heat death of the universe. At this point, all matter will have been converted to the most disordered possible configurations, and no further work can be extracted from any thermodynamic gradient. It is the most stable state possible, but it is also the most featureless, the least interesting, the end of all structure and process and event. But this is beyond any timescale that has meaning to us. For now, the universe is far from thermodynamic equilibrium. Stars are burning, galaxies are forming and evolving, life is maintaining its improbable, beautiful, locally ordered structures against the universal drift toward disorder. The cosmos is still in the middle of its story. The fine-tuning of the universe is one of the most remarkable and most discussed topics in cosmology and philosophy. The physical constants of nature, the numbers that appear in the equations of physics, the speed of light, the strength of gravity, the mass of the electron, the charge of the proton, the strength of the strong nuclear force, appear to be exquisitely calibrated for the existence of complex structure and life. If the strong nuclear force were slightly weaker, protons and neutrons would not bind, nuclei would not exist, and there would be no atoms. If it were slightly stronger, all hydrogen would have fused to helium in the early universe, and there would be no hydrogen-burning stars. If the cosmological constant, the term in Einstein's equations associated with dark energy, were much larger, the universe would have expanded too rapidly for galaxies and stars to form. If it were negative, the universe would have collapsed before structures could form. These calibrations are not understood. We do not have a theoretical explanation for why the constants of nature have the specific values they do. The constants cannot be derived from more fundamental principles within the current standard model framework. They must simply be measured. And the fact that they appear to be calibrated in the narrow range that allows for complex structure raises profound questions. Why are they as they are? Several responses have been proposed. One is that there is no explanation. The constants simply are what they are, and there is nothing more to say. Another is that there is a deeper theory that will eventually derive the constants from more fundamental principles. A third is the anthropic principle. The anthropic principle, in its weak form, states that we can only observe conditions in the universe that are compatible with our existence as observers. If the constants of nature were different in ways that prevented the formation of stars and planets and life, there would be no observers to notice. We observe the constants we do, in part, because we exist to observe them, and our existence requires those constants to be in the range compatible with life. This does not explain why the constants are what they are, but it explains why we observe them to be compatible with life. Any universe not compatible with life would have no one to observe it. The multiverse is the idea that our observable universe is not the only universe that exists. Different versions of the multiverse concept arise in different physical theories. In eternal inflation, a model of the very early universe in which a period of extraordinarily rapid exponential expansion occurred, different regions of the inflating space can stop inflating at different times and with different effective values of the physical constants, producing a vast ensemble of post-inflation universes, each a bubble of space with its own physical laws and constants. Our universe is one such bubble. Most of the other bubbles would have constants incompatible with life and would contain no observers. String theory, a theoretical framework that proposes that the fundamental objects of nature are not point particles, but tiny one-dimensional strings of energy, predicts an enormous number of possible configurations, perhaps 10 to the power of 500, each corresponding to a different set of physical constants. In the string theory landscape, most possible universes have constants very different from ours. If the multiverse is real, the anthropic principle provides an explanation for why we observe constants compatible with life. We can only exist in one of the rare universe configurations where the constants fall in the life-compatible range. These ideas are genuinely uncertain and are not universally accepted among physicists. The multiverse cannot be directly tested, which makes it a matter of ongoing philosophical and scientific debate. But the mathematical frameworks from which it arises are taken seriously by many leading physicists. The idea that our universe is one of many, that the constants of nature we observe are not uniquely determined, but are simply the values that allow for our existence among a vast ensemble of possible values, is perhaps the most humbling and the most expansive thought in all of cosmology. Let your breathing settle even more deeply. The cosmos may be one of very many. The laws of physics may be one configuration among an almost infinite number of possible configurations. And yet here, in this particular configuration, with these particular constants, stars have formed and burned for billions of years and scattered their products across space, and those products have formed planets and on at. At least one of those planets' life has arisen and evolved over billions of years into organisms capable of understanding quantum field theory and the structure of space-time and the arrow of entropy. The cosmos became aware of itself. Carl Sagan created the cosmic calendar as a way of compressing the entire 13.8 billion year history of the universe into a single calendar year, to give us a sense of where we are in cosmic time. In the cosmic calendar, the Big Bang occurs at midnight on January 1st. The first stars form in late January. Galaxies begin to form in February and March. The Milky Way forms around May. Our solar system forms around September 2nd. Life on Earth appears around September 21st. The first multicellular life appears around December 5th. Fish and other vertebrates appear on December 19th. Dinosaurs appear on December 25th. The first modern humans appear in the last hours of December 31st. All of recorded human history, from the first writing to the present day, from ancient Mesopotamia to the moon landing to this very moment, occurs in the last 10 seconds of December 31st. On this scale, a human lifetime of 80 years is less than 1/5 of a second. A civilization of 10,000 years occupies about 20 seconds. Everything you have ever known, every person who has ever lived, every war and discovery and art and music and love story in recorded history, all of it fits in the last few seconds of the last minute of the last day of the cosmic year. The universe spent most of its existence without human consciousness in it, and that consciousness, when it arrived, produced beings capable of reconstructing the entire history of the cosmos from the evidence of light and atoms and physics. In 10 seconds of cosmic time, relative to a cosmic year. The question of consciousness and its place in the cosmos is one of the deepest and most unresolved in science and philosophy. Consciousness, the subjective experience of being, the sensation of having an inner life, is the most immediately certain fact of any conscious being's existence, and one of the least understood in terms of physical mechanism. How the physical processes of the brain, the electrochemical signals, and the patterns of neural activity give rise to the experience of being, of feeling, of thinking is the hard problem of consciousness, and it has resisted a definitive explanation despite enormous advances in neuroscience and cognitive science. What we do know is that consciousness arises from physical processes in biological organisms that themselves arose from the evolution of life, which arose from chemistry, which arose from the elements produced in stars, which arose from the structure of the early universe, which arose from the Big Bang and whatever preceded it. Consciousness is, in this sense, a product of the cosmos. The atoms that think these thoughts were made in stellar interiors billions of years ago. The forces that power the neurons that generate the experience of reading these words are the same electromagnetic force that holds atoms together and makes stars shine. Consciousness is not separate from the cosmos. It is a part of the cosmos that became complex enough to experience itself. You are not observing the cosmos from outside. You are the cosmos, looking at itself. The curiosity you feel when you learn about quantum fields, or the first stars, or the arrow of entropy, is the curiosity of the universe trying to understand its own nature through the brief, temporary, extraordinarily improbable structure that is a conscious human mind. The awe you feel when you contemplate the scale of space or the depth of time is the universe's own awe at its own existence. This is not poetry. It is a description of the physical and biological reality. The matter in your body was made by the cosmos. The energy that runs your brain comes from the sun, which is powered by nuclear fusion, which is a quantum mechanical process, which is governed by the Standard Model, which operates through the quantum fields that permeate all of space. You are continuous with the cosmos. You are a temporary arrangement of the cosmos's own material that has become complex enough to wonder about the cosmos. And tonight, as you rest, that temporary arrangement of cosmic material is returning to a quieter state. The complexity of waking consciousness is giving way to the simpler, quieter complexity of sleep. The neurons are settling. The thoughts are slowing. The body, which has been in continuous motion and activity through the day, is releasing its tensions and resting. The Higgs field is still there, giving mass to every particle in your body. The gravitational field of the Earth is still holding you in place. The quantum fields are still vibrating at their 0-point energies. The electromagnetic force is still holding your atoms together. The cosmic microwave background is still filling space with its ancient 2073 Kelvin radiation. The universe is still 13.8 billion years old and getting older by 1 second every second, and the cosmos, in all its extraordinary depth and richness and mystery, is continuing to exist as it has for 13.8 billion years, without needing anything from you tonight. Your only task is to breathe. And then, when the breath becomes slow and deep and regular, to sleep. The cosmos will still be here when you wake. Every quantum field, every force, every ancient photon, every star, and every galaxy of the 2 trillion galaxies, all of it continuing quietly in the dark. But before we drift there, let us spend a little more time in the deep structure of things, because the cosmos has more to offer the resting mind. Quantum tunneling is a phenomenon that allows particles to pass through barriers that classical physics says they should not be able to cross. In classical physics, a particle that does not have enough energy to overcome a potential energy barrier simply bounces back. But in quantum mechanics, because particles have wave-like properties and their positions are not precisely defined, there is a finite probability that a particle will be found on the other side of a barrier even when it does not have enough classical energy to get there. It is as if a ball rolling up a hill simply appears on the other side without ever having had enough energy to reach the top. Quantum tunneling is not a curiosity. It is essential to the cosmos. The sun shines because of quantum tunneling. At the temperatures in the sun's core, about 15 million degrees Celsius, protons moving toward each other in the plasma have an average kinetic energy that would not, classically, be sufficient to overcome the electromagnetic repulsion between them and bring them close enough for the strong nuclear force to fuse them. But because of quantum tunneling, there is a probability that a proton will tunnel through the electromagnetic barrier and reach a neighboring proton close enough for fusion to occur. Without quantum tunneling, the sun would not shine, stars would not exist, and the cosmos would be dark. The warmth you feel from sunlight is ultimately a quantum mechanical phenomenon. Quantum tunneling also plays a role in radioactive decay, in the function of transistors and microchips, in biological enzyme function, and in many other processes. It is a feature of reality at the quantum scale that has macroscopic consequences at every level, from stellar physics to the computer or device that may be playing this recording. Special relativity, published by Albert Einstein in 1905, begins with two postulates: that the laws of physics are the same in all inertial reference frames, and that the speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the source of the light. From these two simple postulates, an extraordinary range of consequences follows. Time dilation, moving clocks run slow relative to stationary ones. Length contraction, moving objects are shortened in the direction of motion relative to their rest length. The relativity of simultaneity, events that are simultaneous for one observer may not be simultaneous for another. And the equivalence of mass and energy, expressed in the equation E equals mc squared, perhaps the most famous equation in the history of physics. The equivalence of mass and energy is not merely an equation, it is a deep statement about the nature of matter. Mass is a form of energy. Energy is equivalent to mass. When matter and antimatter annihilate, their mass is converted entirely to energy in the form of photons. When the sun fuses hydrogen to helium, the helium has slightly less mass than the hydrogen that formed it, and the difference in mass is released as the energy of sunlight. The mass of a proton is not simply the sum of the masses of its constituent quarks. About 99% of the proton's mass comes from the kinetic energy of the quarks and the energy of the gluon field inside the proton, which according to E equals mc squared, contributes to the proton's mass. You are mostly made of energy in the form of quantum field interactions, with a small contribution from the intrinsic masses of the quarks and electrons. General relativity, published in 1915, extended special relativity to include gravity. Einstein's key insight was that gravity is not a force in the traditional sense, but a consequence of the curvature of space-time. Mass and energy curve the space-time around them, and other objects move through this curved space-time, following the straightest possible paths, called geodesics. The apparent attraction of gravity is the result of these geodesic paths curving toward massive objects due to the curvature of space-time. Space-time is not a rigid background. It is a dynamic, flexible structure that can be stretched, curved, and rippled by the presence of mass and energy. A massive object like the Sun curves the space-time around it, and the Earth follows a curved path in this space-time that we call an orbit. A sufficiently massive and compact object creates such extreme space-time curvature that even light cannot follow a geodesic that escapes. This is a black hole. The event horizon is the boundary in space-time beyond which all geodesics lead inward. Gravitational waves, predicted by general relativity, are ripples in the curvature of space-time that propagate at the speed of light. They are produced by accelerating masses, and the most intense sources are the mergers of black holes and neutron stars. When two black holes spiral together and merge, the space-time around them ripples, and these ripples spread outward at the speed of light. As we discussed earlier, the LIGO detectors measured these ripples for the first time in 2015, confirming one of the last major unverified predictions of general relativity. Stephen Hawking, who died in 2018, had worked on general relativity for his entire career and did not live to see the observation of the black hole image by the Event Horizon Telescope in 2019. Though he knew that the detection of gravitational waves in 2015 had confirmed the existence of stellar mass black holes beyond any reasonable doubt. Hawking radiation is the theoretical prediction published by Stephen Hawking in 1974 that black holes are not entirely black but emit a faint thermal radiation due to quantum effects near the event horizon. The mechanism involves virtual particle pairs that appear spontaneously near the horizon due to the quantum vacuum fluctuations we discussed earlier. Occasionally, one particle of the pair falls inside the horizon while the other escapes. The escaping particle represents energy leaving the black hole, and by the conservation of energy, the black hole must lose a corresponding amount of mass. Over an enormously long time, a black hole will lose all its mass this way and evaporate completely. The temperature of the Hawking radiation is inversely proportional to the mass of the black hole. Smaller black holes are hotter and evaporate faster. A stellar mass black hole would take longer than the current age of the universe, enormously longer, to evaporate. But the prediction is robust and has been confirmed in analogous systems in laboratory settings using sonic black holes. The information paradox is one of the deepest unsolved problems in theoretical physics. If a black hole evaporates completely through Hawking radiation, what happens to the information about everything that fell into it? In quantum mechanics, information is conserved. The laws of quantum mechanics are time reversible, meaning that knowing the complete quantum state of a system at any time in principle allows you to reconstruct it at any other time. But if a black hole evaporates and the Hawking radiation is truly thermal and random, as Hawking originally calculated, then the information about the things that fell in is lost. This would violate quantum mechanics. Something must be wrong. Either black holes do not fully evaporate, or the Hawking radiation is not truly random but carries information in subtle correlations, or quantum mechanics breaks down near black holes in some way not yet understood. This paradox has driven decades of theoretical work, including string theory approaches, firewall proposals, and the holographic principle, but a definitive resolution remains elusive. The holographic principle is another extraordinary idea from theoretical physics. It proposes that the information content of a region of space is not proportional to its volume, as you might naively expect, but to the area of its boundary. This was first suggested by Jacob Bekenstein and Stephen Hawking in the context of black hole thermodynamics. The entropy of a black hole is proportional to the area of its event horizon, not to its volume. The holographic principle generalizes this. The entire information content of a three-dimensional region of space can be encoded on a two-dimensional surface that bounds it, like a hologram. This suggests that the three-dimensional world may be, in some deep sense, a holographic projection of information encoded on a two-dimensional boundary. The AD-S/CFT correspondence in string theory provides a concrete mathematical realization of this idea, relating a theory of gravity in a higher dimensional space to a quantum field theory without gravity on the lower dimensional boundary of that space. These ideas, quantum tunneling and special relativity and general relativity and black hole thermodynamics and the holographic principle, are not metaphors or science fiction. They are the best mathematical descriptions of physical reality that humanity has produced. They have been tested with extraordinary precision in experiments around the world. They describe the actual behavior of the cosmos at its most fundamental levels, and they suggest that reality is stranger and more beautiful and more deeply structured than ordinary experience would lead us to suspect. Let your breath settle. In slowly, out slowly. The cosmos is deep. Its laws are precise. Its history is long. And right now, at this moment, all of those laws are operating around you and through you, giving mass to your particles, holding your atoms together, curving space-time around your mass, keeping you in place on the surface of a world that is orbiting a star that is circling a galaxy. The first galaxies are among the most distant and ancient objects we have observed. They formed in the first billion years of the universe's history, from the dense regions of the cosmic web that gravity was gradually pulling together. These first galaxies were smaller and more irregular than the large, well-organized spiral and elliptical galaxies we see in the local universe today. They were also more actively forming stars, converting their gas into stellar material at rates far higher than modern galaxies. The universe in its first billion years was a time of intense stellar formation and rapid chemical enrichment. Over cosmic time, galaxies grew by merging with each other and by accreting new gas from the surrounding intergalactic medium. Small galaxies merged into larger ones. The beautiful large spirals and massive ellipticals of the local universe are the products of billions of years of merging and accretion. The Milky Way, with its orderly spiral structure, has grown from a much smaller original galaxy by swallowing hundreds of smaller dwarf galaxies over its 10 billion year history. The Sagittarius dwarf galaxy is currently being absorbed by the Milky Way. Its stars spread into tidal streams that wrap around the Milky Way's disk. Other remnants of past mergers are visible as streams and shells of stars in the outer halo. The life cycle of a star is one of the most complete and well understood stories in astrophysics. A star begins as a slowly rotating cloud of gas and dust that collapses under gravity, spinning faster as it contracts. Heating as gravitational potential energy is converted to thermal energy, eventually igniting nuclear fusion in its core when the temperature and pressure become sufficient. In a star like the Sun, hydrogen fuses to helium in the core. This releases energy that generates the pressure that supports the star against gravitational collapse. The star is in a state of hydrostatic equilibrium, the inward pull of gravity balanced by the outward pressure of the hot gas and radiation. This equilibrium lasts for as long as the hydrogen in the core holds out. For the Sun, the main sequence lifetime is about 10 billion years total, of which about 4.6 billion have already passed. When the hydrogen in the core is exhausted, the core begins to contract and heat up, while the outer layers expand and cool, turning the Sun into a red giant. In the red giant phase, the Sun will expand to perhaps 100 to 200 times its current diameter, possibly engulfing Mercury and Venus, and perhaps reaching Earth's current orbit, though Earth may spiral outward as the Sun loses mass. Eventually, the Sun will shed its outer layers in a beautiful, glowing planetary nebula, leaving behind a white dwarf, a dense, hot sphere of crystallized carbon and oxygen about the size of the Earth, slowly cooling over billions of years. More massive stars live shorter lives and die more violently. A star 10 times the mass of the Sun lives only about 20 million years before exhausting its nuclear fuel through successive shells of fusion, producing an onion-like structure of concentric shells of different elements. When the iron core forms, fusion can extract no more energy, and the core collapses catastrophically in a fraction of a second, triggering a supernova explosion that for a brief moment outshines the entire galaxy containing it. The collapse of the core produces either a neutron star, or, if the mass is sufficient, a black hole. The outer layers are blasted outward at a significant fraction of the speed of light, carrying with them the heavy elements synthesized in the star's long life, seeding the interstellar medium with the material for the next generation of stars and planets. Supernovae are one of the most important processes in the cosmos. They produce the heavy elements without which rocky planets cannot exist. They drive shock waves through the interstellar medium that can trigger the collapse of nearby gas clouds and initiate new star formation. They accelerate particles to high energies, creating the cosmic rays that continuously rain down on Earth. And they are bright enough to be used as standard candles for measuring distances across the universe. The discovery of the accelerating expansion of the universe was made using type Ia supernovae as distance markers. The cosmos is not a static backdrop. It is an active, evolving system in which stars are being born and dying, galaxies are merging and evolving, matter is being processed through stellar interiors and scattered back into space enriched with new elements, to be incorporated into the next generation of stars and planets. Everything in the universe participates in this grand cycle of stellar birth and death and renewal. The cosmos is alive in the sense that it is continuously in process, continuously transforming, continuously producing novelty from the same fundamental ingredients under the governance of the same fundamental laws. Let your body rest completely now, the muscles in your face soft, your jaw unclenched, your neck and shoulders released, your arms heavy, your chest rising and falling gently, your legs still, your breathing slow and quiet. You are made of the products of this grand cosmic cycle. The elements in your body are borrowed from the cosmos and will be returned to it. Right now, in this moment of stillness, you are the cosmos resting. The cosmos has been doing extraordinary things for 13.8 billion years. It has made hydrogen and helium in the Big Bang. It has assembled them into the first stars. It has burned those stars and scattered their nuclear products. It has built galaxies and the cosmic web. It has made the sun and the earth and the moon. It has produced life and evolution and consciousness. And now it is resting briefly in the form of you, in this room, on this night. Sleep now. You are the cosmos resting, and that is enough.